Hey everybody! When we left off last time, I went over the periodic table. We reviewed some of the elements that are particularly relevant to human physiology. So let's take a look at those. We have hydrogen, sodium, magnesium, potassium, calcium, iron, carbon, nitrogen, oxygen, chloride, and iodine. And of course there are others that are important as well. I asked you when we left off in the last video to pick at least 2 or 3 of these, and using the information in the periodic table, try to determine how many protons an atom would have, how many electrons that atom would have, if it was a neutral atom, and whether or not there would be neutrons in an atom. So let's take a look at a couple of these. If we look at sodium, sodium has an atomic number of 11, which means we know that it has 11 protons. Since the mass is higher than 11, we know that it has some neutrons. And if we assume that this atom is neutral, then we know that it has 11 electrons. And remember that all atoms start electrically neutral. That's going to change, and we'll talk about that in a minute. If we take a look at oxygen, oxygen has 8 protons. The mass is higher than 16, so we know that it has some neutrons. And assuming that this atom is neutral to start, it would also have 8 electrons. Now, if you've taken chemistry before, you've probably learned it can get pretty complicated with figuring out where those electrons are located. And so you learned about different shaped orbitals as the atoms got bigger and bigger. We're going to keep things really simple because in the end, what we really care about for physiology is whether or not that atom is going to want to react with another atom and therefore give us some kind of bond or chemical reaction and something's going to happen, because that ultimately is physiology. So what we really care about is how many electrons are in the outermost orbital or outermost shell. The rule of thumb for atoms is that we have in our nucleus the protons and neutrons. The first orbital can hold a maximum of 2 electrons. The next one can hold 8, and then 8, and then 8, and so on. So we call that the 2, 8, 8, 8 rule. Now, if atoms get really big, it starts to get more complicated than that, but fortunately for these really big elements down here, we don't tend to see those as much showing up in the body. In fact, typically not at all. So let's see what actually happens when we take some of these elements and draw an electron configuration, which is what that is, for that particular atom. So let's take a look at sodium. We said that sodium has in the nucleus 11 protons, and we know that there are some neutrons. If we assume that this atom is neutral, then we're going to have 11 electrons. So my first orbital is going to have 1 here and 1 here. Since they're both negative, they want to stay away from each other. My second orbital can hold a maximum of 8. So at first I'm going to kind of try to spread these guys out, but once I get 4 on there, I want to actually pair them up. Now we know that they're not going to pair up in real life because these negative electrons are going to repel each other, but for convention's sake, we're going to draw them paired up, because it's going to make it really easy for us to tell if we've used up all of our electrons. So let me show you how that works. So we've got 4, we need to have 8. So 5, 6, 7, 8. So we now have 2, 4, 6, 8. We know that shell is full. And then we had 2 in the middle, so that's going to give us 10. We know that sodium has 11 protons and 11 electrons, so we're going to stick another orbital on here, and we're going to put 1 more electron out there. So what I have just drawn is an electron configuration for a neutral atom of sodium. And you'll notice that it only has one electron in that outermost shell. And that's going to be really important in a little bit. So let's pick another atom here. Let's do carbon, since we said that carbon is so important here. Carbon, we know here, has this atomic number of 6. So let's draw an electron configuration for a neutral atom of carbon. So if carbon has 6 protons, we're going to stick 6 protons in the nucleus. It had a mass of 12, so it will have some neutrons. And then if we assume it's neutral, it will have 6 electrons. So we put 2 in the first orbital, and then we go to the second orbital, and we put 3, 4, 5, and 6. So this would be an electron configuration for a neutral atom of carbon. Now if you notice, this outermost orbital right here has 4 electrons in it. Again, that's going to be really important in a minute. Let's try hydrogen. So let's take a look back here at hydrogen. Hydrogen has an atomic number of 1, and it also has a mass of about 1. So we're going to put 1 proton in the nucleus. Now, would it have any neutrons? If it has a mass of 1, well, that mass of 1 is already taken up by that 1 proton. So a hydrogen atom does not have any neutrons in it. It's going to have 1 electron, so we're going to put that in the first orbital. There. And remember, this first orbital only needs 2 electrons to be full. Let's try another one. Let's jump over here and let's try chloride. Chloride has an atomic number of 17 and a mass of about 35. All right, so if we do chloride, we know it has an atomic number of 17. So we're going to put 17 protons in the nucleus. The mass was about 35, so we know there are neutrons. And if we assume it's neutral, we need to put 17 electrons. So we're going to put 2 in the first shell. How many in the next one? Right, we're going to fill it up with 8. So we're at 10. We need to get to 17. So we've got 11, 12, 13, 14, 15, 16, and 17. Now, this outermost shell right here is always called the valence shell. Since we have to fill an orbital before we can go to the next one out, we're really interested in how many electrons are in that valence shell. And that valence shell is going to determine if the atom is reactive. So does he want to interact with another atom? Now, the thing that you need to understand is that atoms they desperately want that outer orbital to be full. They really want it to be full. If it's full, then they want to be left alone. So if we take a quick look at the atoms that we have here, we have sodium, carbon, hydrogen, and chloride. Are any of these atoms happy? Well, they're not, because none of them have a full outer shell. They're going to want to interact with somebody else in order to become happy, in order for that valence shell to be full. So let's take a look at carbon. Just change up our colors here. So carbon, we said, has 4 electrons. It wants this outermost valence shell to be full. It would be full if it had 8 electrons. So it's going to need 4 more in this outer shell to be full. Now, carbon can interact with a lot of different atoms. It can share electrons with other carbons, with oxygen, with nitrogen, all kinds of things. But because I'm a lazy chemist, because remember, not a chemist, I'm going to take this nice little hydrogen here who has 1 electron, meaning he needs one more. And I'm going to spackle him on here. And now this hydrogen has 2 electrons. He only needs 2 to fill that first shell, so he's happy. So if we put another hydrogen over here, now this hydrogen is happy because he's got 2 electrons. If we put another hydrogen over here, now this hydrogen is happy with 2 electrons. And if we stick one more hydrogen over here, this hydrogen is happy and has 2 electrons. In addition, my carbon now has access to 8 electrons in that outermost shell, and we have created a molecule CH4. Now, there are a lot of different rules for when carbon would bond with one type of atom or another, and because we're basically trying to cover all of inorganic and organic chemistry in a week, maybe less, something like that, you're going to need to take a chemistry class if you really want to dive into the nuts and bolts of what will happen if carbon interacts with different types of atoms and when. Let's take a look at hydrogen over here. Now, hydrogen could interact with things like carbon, or he could just share an electron with another hydrogen, right? And that would give us a molecule of hydrogen. He could, if we had an oxygen atom, which we don't have drawn over here, so let's flip back here for just a quick second. Oxygen has 8 protons. So let's draw an oxygen atom really quick. He's got 8 protons. He has some neutrons, which means he's going to have 8 electrons, 2 in the first shell, 3, 4, 5, 6, 7, 8. Oxygen needs 2 more atoms, or 2 more electrons, in order to be full and happy. So we could stick a hydrogen on here, and this is our oxygen. And now these hydrogens are happy because they each have 2, and oxygen now has 8, so he's happy, and you have created water. Now if we look over here at our sodium and our chloride, we have a problem. Now, chloride could share with a hydrogen. I could put a hydrogen on here and create hydrochloric acid, or hydrogen chloride. But sodium has a real problem. Sodium needs to get to 8 electrons, but it only has 1. Now I like to think of atoms like toddlers at a playground, all right? If a toddler or a kid goes to a playground with 1 piece of candy, what are the chances that if he offers to share that 1 piece of candy with somebody else, they're going to give him 7 in exchange? That's not going to happen. Now, I have 2 kids, so I can vouch for the fact that with kids, one of the most important things to them growing up is always fairness. Everything needs to be fair. If you give me 1 piece of candy, I'm going to give you 1 piece of candy in return. Atoms are the same way. So, if we look at sodium up here, he's only got 1 electron, which means he can only get 1 electron in return from somebody else. That's only going to get him to 2, and that's not enough. And he really, really, really wants his outermost shell to be full. So what sodium's going to do, and really any atom that has fewer than 4 electrons out here is going to do, is he's just going to lose that electron. He's going to get rid of it, ditch it. This now has become his valence shell, and it's full with 8, and he's happy. But we did something. Sodium had 11 electrons, but now, it had 11 protons, and still does, but now it only has 10 electrons, which means it has 1 more proton than electron, right? 11 minus 10 is plus 1. So basically there are 11 pluses in this atom and only 1 minus, only 10 minuses. If there are 11 pluses and 10 minuses, that means my sodium atom now is a little more positive. So he has a +1 charge, and we say that he is an ion. Specifically, if it's a positive ion, it's called a cation. And you can remember that because it looks like it has a plus sign right in the name. Now let's go back to chloride for just a minute. We said the chloride could share with a hydrogen, but remember way up here, this guy just ditched an electron. He got rid of it, he doesn't need it, he threw it on the ground. Okay, it was a piece of candy he didn't want. Well, chloride could share with someone else, or why share when there's a perfectly good electron just laying on the ground? Nobody's using it, it's still in the wrapper, mom won't notice, right? So I could grab that electron and take it for myself. Now what's happened is I have 17 protons, 17 pluses, but now I only have 16 minuses. So, I have 17 pluses and now I have an extra, right? I have 18 minuses. So 17 minus 18 is -1. I have one more electron, one more negative than plus. So my chloride is often found with a -1 charge, or with just a negative charge. So this is also now an ion, because anything that's charged is ionic, or an ion. This is an anion because it is negatively charged. So if an atom loses electrons, it becomes a positive ion, or cation. And if an atom gains electrons, it becomes a negative ion, or an anion. What I want you to do now is I want you to go back to the periodic table. So let's jump back there. And let's pick out a few atoms to practice with. I want you to draw electron configurations for the following atoms. And a couple of them we've already done, but don't look at your notes and see if you can redo them yourself. So let's do potassium, calcium. Let's do oxygen and hydrogen again. And let's see, let's go ahead and do chloride again. All right, so practice those, and then in the next video, we're going to kind of put some of those things together and start forming attractions or bonds.